Everyone. We proceed with the second lecture by Sergei Gukov on invariance of three manifolds. Sergei?
Thank you very much, Ludmil. Again, thank you everybody for coming back, and those attending in person. Hello, I cannot see you, but I hope you can see me or hear me. So let me share the screen. Go to the full screen mode. So this will be part two of this lecture series. So my main goal yesterday was to introduce a certain class of objects. So we started easy with tables of integrals, and in general, throughout the first talk, there were all kinds of integrals which were changing integrand depending on topology over knot or link, but in a nutshell, it's all different integrals. And we saw that they're invariant under Kirby moves, and then we connected these integrals to various other topological invariants. So since they're invariant under Kirby moves, they represent some invariants of three manifolds. So we kind of tried to ask, how do they compare to other known things? And we saw that they interpolate between Rokhlin invariants and correction terms of Higard-Floer homology, Turaev torsion, which is also labeled by spin C structures, and various other things. So while yesterday main goal was to define an object so we can talk about it, today we'll explore properties of this object, and we'll see in full glory something that I try to advertise as essentially a deeper theme for these two lectures, namely that it's a crossroad of many different subjects in mathematics. So if yesterday we mainly saw topology and a little bit of quantum groups at generic Q, which is natural since we were trying to define Q series for generic Q inside the unit disk, today we'll also see deep and interesting connections to enumerative geometry and vertex operator algebras, a little bit of mathematical physics, and a little bit of gauge theory. So yesterday, I apologize for making my motivation part very short. I gave you only one motivation for defining this set of invariants. So now, once that definition is out of the way, I can actually spend a little bit more time and elaborate and give you a couple of other motivations or set the goal of constructing this set of invariants. So one motivation has to do with the representation theory, something that was completely behind the scenes yesterday. And since we're trying to associate some Q-series invariants to close three manifolds, it's natural to ask what they have to do with quantum groups at generic Q. Yesterday, we already saw that the answer probably is a lot, because the most efficient way of defining them, which we were able to do for many infinite families of knots and links and pretty much everything up to 10 crossings, did involve quantum groups at generic Q. And then I showed you also the definition based on Rosansky-Witten theory, which used affine Grassmannians as target space. Yeah. And this, yes, hello? And this connects very nicely to use of affine Grassmannians in relation to quantum groups, not only at generic Q, which was the main focus or interest in our discussion yesterday, but this relation has been actively studied at roots of unity, which in some sense is easier, where various subspaces such as slices and affine Grassmannians or affine Springer fibers and closely related objects appeared in various previous works, which fit very nicely in connection to generic Q that we were discussing yesterday. And this picture already appeared in some form from topological perspective, but you can actually try to analyze this geography of the Q circle or Q disk from the point of view of representation theory, thinking about what kind of geometry is responsible for different forms of quantum groups. So that was a representation theoretic motivation for studying this Q-series invariance. Another one is more from the TQFT perspective or rather gauge theory perspective, where I want to point out a close cousin of this Q-series invariance in one dimension higher, namely in dimension 4, which is known as Vafa-Witten partition function, or various problems involving sheaf counting on complex surfaces. So it shares many features with what we were discussing before, and in fact was main motivation, or one of the main motivations in the original paper of Pavel Turaev, myself, and Kumran Vafa, where we actually defined this Z-hat invariance using connection to Vafa-Witten theory. And not surprisingly, therefore, they share many similar properties. For instance, Vafa-Witten invariance of 4 manifolds are hard to define in general. So there is a physics definition, at least in principle, for arbitrary 4 manifold, but explicit mathematical expressions or constructions are only known for Kähler surfaces. Another feature that they share in common is that Vafa-Witten invariants are not just invariants of 4 manifolds, but 4 manifolds with additional structure, or rather decoration, if I were to use language of decorated TQFT. And this is a close cousin of spin C structure decorations that we saw for the other invariants. And last but not least, the Vafa-Witten invariants turn out to be interesting modular objects. In particular, they turn out to be characters of various vertex algebras, which one can associate to a 4 manifold, and these have physical interpretation, as well as basically pave the way to connecting vertex algebra to this subject of manifold invariance. And again, the Z-hat invariants, this Q-series invariants we were discussing yesterday, share many similar properties, and in many ways they're actually easier because, as you might expect, in dimension 3, it's easier to topology is simpler, and the corresponding TQFT is simpler. So for this reason, it's much more computable. So it's easy to compute again. It's in many infinite classes of links and nodes, and basically you can easily cover everything up to 10 crossings. So I'm sure with further developments, we'll have even more efficient formulae for this Z-hat. So that's already pretty clear. They have integer coefficients because they're supposed to be counting dimensions of graded dimensions of some homology groups, labeled by spin C structures. That's similar to labeling of Vafa-Witten partition functions. And again, last but not least, something we'll discuss a lot today, they turn out to be characters of vertex algebras, very much like original Nakajima's observation about sheaf counting on complex surfaces. What's interesting is that they'll turn out to be characters of fairly exotic logarithmic algebras, which is actually good because this is basically the cutting edge discussion in the VOA community. These vertex algebras have non-semi-simple representation categories and are often called logarithmic vertex algebras. I'll say a little bit more about this as we proceed along, but this could be viewed as another motivation of constructing this invariance, analogous to Vafa-Witten invariants of 4 manifolds that have been studied in the past 25 years. And again, progress is relatively slow because this is hard, and for manifold topology is hard. But here I mentioned some of the recent works on the subject. Again, feel free to interrupt me at any point if there are questions. If not, I'll proceed to main part of this talk. So I gave you a few motivations for studying this Q-series invariants from several different perspectives. But now that we know how to compute them in many examples, and we have a sort of rough picture of where they belong in the world of mathematics, for example, through representation theory or three-dimensional topology, it's good to start getting ourselves a little more familiar with these objects and discuss their properties. So they depend on 3 pieces of data. So they, of course, depend on the choice of 3 manifold, which could be either closed or in the process of building this invariance, we saw that it's important to construct this invariance for manifolds with boundaries, for example, for complements of knots and links, and then glue them together in a closed manifold. So dependence on M3, we discussed extensively yesterday. That's where invariance under Kirby moves enters the stage and is crucial for showing that this is a topological invariant. We also talked to some extent about dependence on these additional decorations. This is also important because if you want to build this by cutting and gluing, what you're dealing with is a decorated TQFT, not the usual TQFT. Again, it's not rocket science, but it's an important point, and actually that's something that's play an important role in connecting this Q-series invariants to various other invariants labeled by spin or spin C structures that we saw yesterday. That's part of my title. Rokhlin and Turaev, they both are labeled by spin structure for Rokhlin invariants and spin C structure for Turaev invariants. So connection comes through these additional decorations. And for instance, this power delta B yesterday was interpreted as something related to correction terms of Higard-Floer homology. And again, this is where B dependence is important. What we'll discuss today is a third aspect of this sort of invariance, namely dependence on Q. We'll ask, what kind of function of Q do we get? So if I were to summarize purpose of today's talk, that's probably the main aspect. We'll discuss properties of this Z-hat Q-series for generic three manifolds. We'll look a little deeper into the integral nature of the integer coefficients here. As I mentioned yesterday, this was another motivation to relate it to categorification program and make this invariance categorifiable so that they can be realized as creditor characteristics of homology groups. And this is the kind of question, dependence on Q, that will lead us to discussion of enumerative invariance and vertex algebras at great length. So this is a quick summary of what we saw yesterday, something already mentioned in words. So this invariants live inside the unit disk for generic value of Q in absolute value less than 1. In the geography of decorated TQFTs, they're labeled by spin C structures and related to various other TQFTs labeled by either spin or spin C structures. If you sum over spin structures, you may get various other TQFTs which are either not labeled by anything at all, like WRT invariants of three manifolds, for example, require no additional decorations, or you may get some connection to logarithmic invariants of three manifolds, which also require certain decorations. However, not a choice of spin or spin C structure. They require additional choice of decoration in H1, which you can recover by Fourier transforming spin C structure in a suitable way. So this is something physicists might call bosonization, because spin disappears, but you still have certain dependence on additional data. Anyway, this is quick recap of most of the discussion yesterday. I didn't talk about this part, but now I wanted to mention the name logarithmic or non-semi-simple because this will make several appearances in today's talk, and there is a much deeper meaning to it. So let's backtrack a little bit. And yesterday I showed you many ways to compute this invariance. So let's start with simple examples. Let's look at what computations or formulae look like. For instance, one particular three manifold you can construct as a surgery on a trefoil knot and with a different surgery coefficient on a figure 8 knot. So of course, if what I told you is not a lie and we really get invariant of a three manifold, you should see explicitly that since these two are related by Kirby moves, you get the same answer. And of course, as an independent check, you can see that that's the case. That's fine. That's a good example. But let's now look at manifold with reverse orientation. So this is a question that's relevant to the very beginning of my talk yesterday, where I started with a simplifying assumption that something was definite. And then I was gradually relaxing this assumption throughout the talk yesterday. But actually now I'm doing something complete opposite in some sense. If this was definite in one way, then this is definite in complete opposite way. So within assumptions of beginning of my talk yesterday, this would be complete opposite choice. And let's see what's happening. So using techniques that I mentioned yesterday, you can actually compute this invariance now for both orientations. So these assumptions could be relaxed, but let's see how they're related. So in both cases, you get a Q hypergeometric function. So this is a very nice series, and this is another nice one. And I invite you to do the following thing. Try to replace Q by 1 over Q in every term of the first sum, and multiply every term in the sum by sufficient power of Q, so that you have no inverses of Q. So you replace Q by Q inverse and then multiply by sufficient power of Q. So again, everything is expressed in terms of Q rather than Q inverse. What happens? You get exactly the second sum. So this is some quick calculation which involves only dealing with every single term of the sum in general, and you can basically do it on the back of the envelope. So I invite you to play with this. So what we learn from this is that this Q-series invariant of a 3-manifold and 3-manifold with opposite orientation are related by this procedure of going outside the unit disk, namely replacing Q by 1 over Q, but not in a silly way where the answer is just going to be a function of Q inverse rather than Q, but in a smart way, in the sense that both are expressed as Q series, but they're meant to be analytic continuation of one another outside of unit disk in the Q plane, or from upper half plane to lower half plane in terms of variable tau, where tau is the usual modular parameter related to Q in standard way, where Q is exponential of 2 pi I tau. So this is good, and as you can see, this even has meaning for topology, because if you want to know how these invariants are related for manifolds with opposite orientation, well, you want to know how to go from inside unit disk to outside the unit disk. You have to have good control over the analytic properties of this function. You have to know what kind of function it is. So this has been investigated a little bit. So here are some of the early papers on this subject, but a lot more needs to be done. And as I'll show in the slide, basically we just scratched the surface so far in understanding of the subject. So if you have a plumbing graph, here I'm going back to a very simple class of manifolds, this plumbing graphs that I used in the very beginning of my talk yesterday as an illustration. So if you have plumbing graph, which consists of only one trivalent vertex and 3 legs, this corresponds to 3-manifold, which is a ciphered manifold with 3 singular fibers. You end up with modular objects. In fact, this is an example of it, of modular weight 1/2. And the corresponding Q-series expressions that you get turn out to be characters of logarithmic vertex algebras. So again, compared to case of Vafa-Witten partition functions, where Vafa-Witten invariants, at least in some cases, are known to be identified with characters of usual vertex algebras. So here they turn out to be related to logarithmic ones. In this family, the simplest member is Poincare sphere, and actually that's the example which was analyzed from the perspective that in modern day we would call recursion analysis by Lawrence and Zagier back in 1999. And what I'm going to present in this later columns is basically generalizations to, first of all, this entire class of ciphered manifolds, and then slowly increasing complexity, which was done in series of works by Catherine Brinkman, Carl Malbrook, Anton Milish, also in our team with Miranda Cheng, Song Chung, Francesca Ferrari, Sarah Harrison, and many other people I should include in this list, of course. So this is ongoing program, but we didn't get very far, as you can see. So first of all, analysis has been generalized to ciphered manifolds with 4 singular fibers, where you face already much higher level of complexity. This leads you to the world of weight 3/2 modular objects at the level of Q dependence. And at the level of vertex algebras, you can still match this with characters of logarithmic vertex algebras, but they turn out to be new logarithmic VOAs. And some of this is actually work in progress with Boris Fagin and this team. And then we're just starting as far as plumbing manifolds go. But as soon as you get to something which has, for example, two or more high valency vertices, for example, 2 3-valent vertices, you immediately get in a stratosphere of this quantum modularity or logarithmic VOAs. For example, in a very nice paper by, again, Catherine, Carl, and Anton, they showed that even in this basic case where you have just 2 vertices, you immediately get so-called high depth modular objects. And I have no clue what the corresponding vertex algebras are associated to it. So I think that's a great question. And from the 3-manifold topology, we're just getting started because this is a warm-up case. We're barely getting outside of Seifert manifolds. And as you can see, things get progressively more interesting and there is a lot of work need to be done. The example or class of examples that I mentioned yesterday, for instance, I showed that you can compute this Q-series. There is nothing stopping you in doing it very efficiently for pretty much any surgery on any knot up to 10 crossings. So one of the examples that I showed yesterday, and I'll come back to it, was this particular simplest surgery on figure 8, where you can compute hundreds of terms in this Q expansion. Something I advertised yesterday is that I have no idea what kind of Q-series it is. This was posed as a question for at least 2 years. So there was Q-series and you could compute it to any number of terms using the recursive procedure that we provided with Cyprian or method of Sanyuk-Park, for example. But it's not clear what the Q-series was. So that, and then of course there are many of such things, and that's important for understanding connection to vertex algebras. The conjecture is that it's always connected to vertex algebras. And in this case, you can show that it's going to be of a class that's not really simple in terms of VOA terminology. This is not C2 cofinite vertex algebra, or rather logarithmic vertex algebra. And question then is, how do we even approach this sort of question? So this is something that I'll try to explain today. So here, maybe before I move on to this more complicated examples, I want to say a few words about what logarithmic vertex algebras are. So here you see some names, for example, singlet log VOA 1, p. So what does that mean? Well, perhaps more familiar vertex algebras of standard type, the way it was formalized by Borchards, are lattice vertex algebras associated to lattices. And if you consider lattices to be root or weight lattices of Lie algebras, then you can construct affine W algebras also labeled by the same Cartan types. So these are on the left and right side, these are not logarithmic, these are usual vertex algebras. So the logarithmic ones, these more interesting ones, whose characters are not actually modular, but rather mock-modular or more generally exhibit more interesting types of modularity, are singlet and triplet logarithmic VOAs. And they're constructed as follows. So I'll give you, there are many constructions, but I'll illustrate this in a construction of Fagin and Tipunin, where I remind you that some non-logarithmic vertex algebras or new vertex algebras can be constructed out of known ones by considering cohomology with respect to so-called screening operators. These are operators that square to 0 and act as differentials. And Felder, in his famous construction of minimal models, applied this construction by taking cohomology and producing minimal model VOAs. I'm referring to Giovanni Felder and work in early 90s. So Fagin and Tipunin basically proposed to take a kernel of a screening operator rather than cohomology. So this is not as nice operation, obviously. And the result of it is that we're going to get something which has many, many properties shared with usual VOAs in the sense of Borchards, but has some of the axioms relaxed. In particular, in terms of analytic properties, you're going to see logarithms, or in terms of representation theory, you're going to see non-trivial extensions and non-semi-simple tensor categories. So if you apply this construction to lattice VOA, you get so-called triplet. And if you further take invariant part with respect to affine algebra acting on the triplet, you get so-called singlet. So singlet, as the name suggests, is invariant part. So these two logarithmic VOAs sit in between of the perhaps more familiar ones. So this is just to give you an idea of what logarithmic vertex algebras are. So conjecture is that in general, for any three manifold, closed or open, it's of course easier for closed manifolds. This invariants that we discussed yesterday should be characters of logarithmic VOAs. And what we related to correction terms labeled by spin C structures yesterday with deltas, now from logarithmic VOA perspective, we'll have another interpretation. They can be interpreted as conformal weight of the corresponding module, such that the z hat is basically the trace of that module. And again, integrality of coefficients, of course, would be natural because these are characters. So how would we identify what kind of logarithmic VOA corresponds to this? This is actually simplest example. Again, you can do it for many nodes with 10 crossings and more, and all kinds of surgery. So again, this is just beginning of the story in terms of topology. So how would we identify what object this is? So that's the problem I asked many of my friends 2 years ago, in fact, offering bottle of wine, and then still it was unclaimed for 2 years. Again, you can compute these coefficients to any precision. You can feed this in database of integer series and nothing really comes out. So it wasn't clear. So here is the answer. The answer is that you can write this Q series as a sum over 6 different natural numbers, I'll call them GI, such that each term in the sum is Q to the quadratic form with this particular matrix of size 6 by 6, and Q to Q-Paheimer symbols of DI, product of them in the denominator. So that's the answer. This is what this is. It's a very closed form expression. And of course, it's no surprise that for 2 years, it was hard to guess this sort of metrics. And there are some linear terms that I'm meeting here. So any questions so far? So in the rest of the talk, my goal is to tell you where this is coming from. And of course, I'll keep this as a concrete example in mind, but my goal is to explain the underlying mathematics so that you can easily do it yourself for any other example. And then I'll pose some questions in the end. So, yeah.
There are negative coefficients, and so how do you get it?
Oh, this is very, that's right. So there are two things going on here. So first of all, negative coefficients in this logarithmic world are not too surprising. So this is quite standard. And secondly, in this expression, I'm emitting some small, but not some important maybe to some aspects detail, in particular to your question, that to get from this expression to this expression, I should write 1 over Q infinity here. So it also has eta function in the denominator. So this is going to be the numerator. We divide it by Q infinity, and then this particular expression will actually have only positive coefficients. Yeah.
To num sums is this formula?
Oh, this is a great question. Let's revisit this question together in exactly 15 minutes. The answer will surprise you. It's surprising because you would expect that the answer should be yes or no, right? It's a very concrete question, but I claim it's more interesting than that. So let's look where this comes from. So first surprise is that, well, or a natural question, how did I get it, first of all, after all these 2 years, where did it come from? And it came from a completely different field that involves curve counting. So imagine that you have a Calabi-Yau threefold. One of the simplest curve counting problems involves integrating over moduli spaces of stable maps from some genus G surface into a Calabi-Yau, where you have to fix the topological type of the map, namely you fix the degree, sometimes denoted by beta, but I'll consider only one example where this degree could be integer, just integer number. This Dramafit and invariants are in general rational numbers. In fact, the example I'll show you on the next slide clearly illustrates that. And again, it's not too surprising because these are not counts of embedded curves or some specific objects. which have nice deformation abstraction theory, but rather we are counting stable maps, and as such, there are denominators basically related to automorphisms. So the example I want to consider is O-1 plus O- bundle over CP1. This is one of the simplest non-compact local Calabi-Yau manifolds, and a theorem which has several different parts which were proven at different stages of the subject, says that Gromov-Witten invariants of this particular Calabi-Yau have the following form. Again, here there is only one class in H2, namely the degree with respect to this CP1 and the target. That's what I'm going to call D. There is a genus, and therefore Gromov-Witten invariants depend on genus and the degree. For genus 0, the answer was known in early 90s, thanks to work of, this is sometimes what's called Aspinwall-Morrison formula, which was a little heuristic, but then it was proved very rigorously using localization techniques and various other tools, and that's the famous 1 over d cubed. So explicitly you see that it's a rational number. Then in genus 1, you have 1 over 12d, and in the higher genus, this was done by Fiber and Pandre, and the answer expressed, again, it's of course, you can see explicitly, it's not an integer, it's a very fractional number, and it's expressed through Bernoulli numbers. So it's a very concrete count of curves, and you may naturally ask, what does it have to do with 3 manifolds, let alone all these delicate spin C structures, Rokhlin invariants, and other things we're discussing? Well, here is the first clue. That's another theorem that if you consider 3 manifold, which is a 3-sphere, and consider the generating series of this Gromov-Witten invariants, and Gromov-Witten theory, this is called Gromov-Witten potential, summing over genus with parameter h bar, and summing over degree with a variable that I'll call a. This variable will stay with us through the rest of the talk. What you get is a version of quantum trilogarithm. So first of all, this is already a nice, neat fact, part of this theorem. But more importantly, what you get is a WRT invariant of a 3-sphere, where the map of the parameters from Gromov-Witten count of curves to TQFT notations of WRT, same way I used them yesterday, is such that the level here, this order of the root of unity, K, corresponds to the parameter h bar in the Gromov-Witten series, and variable a that counts the degree has to do with the rank of SLN, Rushetikhin Turaev Witten invariants of a 3-sphere. So this variable a is something that prominently features in Homology polynomials of knots, and for this reason, I'll call it Homology PT variable, and again, it will be the star of the show for the rest of our discussion. So this is a theorem that had all the ingredients, important ingredients in a paper of Gukov. In fact, in the form I stated it here, it's basically proved there, but it can be generalized to various other toric Calabi-Yau manifolds, and this was done in a series of works in late 90s. Early 2000s. Fast forward 20 years, this development here was beginning of the relation between quantum group invariants of 3 manifolds on the one hand and curve counting on the other hand. This particular rewriting was beginning of expressing everything through integer invariants rather than fractional invariants. In particular, everything you see in the second line is obviously integer, but claim is that that's actually possible for marginal 3 manifolds. And this is actually where the Z-hat invariants that I mentioned to you are coming from. But I want to highlight yet another development, again, roughly 20 years fast forwarding the history. What it led to is a completely different way of encoding or connecting topology, in particular a topology of knots. So that's part of this correspondence to motivic or whole algebra type structures that we see in Donaldson-Thomas theory. This is integral version of Gromov-Witten curve count that I mentioned on the previous slide. And this is the quiver. or whole algebra associated to the quiver. So what this young gentleman proposed is to remove the intermediate ingredients in this long chain of relations and just view this as a correspondence between nodes on the topology side and a combinatorial data of quivers on the representation or Donaldson-Thomas theory side. So again, this rests on integrality properties, which you see here in the abstract. And the main tool for them was Homology PT homology, or rather colored version of it, which again, you can see even from the abstract of the paper. So I'm not going to do in-depth review of this fascinating subject that's also been going on for past 5 years or so, but I'll give you a glimpse into it, and I'll try to explain the most essential features in particular, so that I'm able to circle back to this Q-series invariance of 3 manifolds at heads by the end of the talk. So the correspondence very roughly says that to each node, you should associate a quiver, or more precisely, some equivalence class of quivers. It may not be unique. And equivalence relations are reasonably well understood. And first, again, once you see something first time, you may ask, okay, how does it look like, which way it goes? So here is an illustration for a very simple example, namely trefoil node. It has quiver, or one of the quivers, with 3 nodes. And again, experts in the subject can explain to you how to reconstruct it and so on. I'll just say that it encodes a lot of topological information about the node, in particular, even homological data, which is related to this variable t that only briefly appeared yesterday and has to do with the homological degree and categorification. So I mentioned it a couple of times yesterday, but here it will appear more prominently. So just to say that this quiver is an extremely meaningful and valuable object from the viewpoint of node. And here how it looks like. For example, Homology PT homology or super polynomial of this trefoil node has 3 terms. So these are the terms in the super polynomial, or the generators of the Homology PT homology. And it's not an accident that this quiver has 3 nodes. So this 3 and this 3 are the same. So that's one piece of the dictionary. Another piece of the dictionary that you can see is that t degrees here are 0, 2, and 3. And this matches the diagonal values of the quadratic form, which is expressing the adjacency metrics or connectivity of this quiver. So in the rest of my talk, I'll mostly focus on this quadratic form, which is somewhat analogous to quadratic form that we use for Plumbing graph, but of course it's very different. So don't get confused. This C will play a very different role from Plumbing graphs.
So it's always symmetric. Yeah, there is a 2-dimensional Calabi-Yau behind.
Yes, yes. I'm not sure if you allow moves or equivalences which make it asymmetric. If Piotr is on a call, he may interject a comment whether this is allowed, but as far as I know, that's what one wants.
What I can say, it's always symmetric, at least in all examples, also infinite classes that are understood.
And do you understand the BPS Lie algebra of that category? I mean,
well, it's cohomological whole algebra according to
no. Cohomological whole algebra, it's a rough invariant. There is a deeper constructed by Davison and Meinhardt, which is a graded Lie algebra.
Oh, I see. Yeah, so that I think is a great question. As far as I know, it's mostly open. So again, Piotr can correct me, but yeah, this is going to the refined direction, yes, normative direction.
That's right.
So I'm glad that it's generating active discussion. There is more to be said, and I hope we can all chat after the talk about it. So as you can see, Piotr and others are even more experts on this and can tell you more about it. So this is a brief summary of various algebraic objects on the quiver side, or enumerative objects, maybe I should say, if we think about curve counting or DT invariants behind this, and various topological data of knots on this side. So all that's going to be relevant to me is that this is an active program that has been, again, going on for about 5 years, and a lot has been done to this dictionary. Many people contributed, so this is just a small sample of various influential papers on the subject, including Markus Tosic, Paul Wedrich, Tobias Ekholm, Piotr Kucharski, who was a collaborator on the original work, Pietro Longhi, and many, many others. So one of the main statements in this correspondence is that if you take colored Homolgy polynomials, or you can do the same thing with homology and super polynomials, and sum them over color, and here is the color. So remember, there was this Homolgy variable A, there is a Q. So what you get is some generating series, which some object that depends on X, A, and Q. So claim is that you can rewrite that series as generating function, generating series in the sense of Koha or quiver partition function, which has this form. Most importantly for me, it has quadratic form in the power of Q. So that's the metric C. It's the same matrix that was defining the quiver. That's basically the connectivity matrix of the quiver. It has the same Q-Poheimer symbols that you saw in the expression that I showed you earlier. So when I said that I'm going to rewrite z hat in this form, which has something quadratic in the exponent, some linear terms, and Q-Poheimers in the denominator. So that's exactly what this program proposed, and it's one of the hallmarks, I would say, of this knot quiver correspondence, which is basically quiver form of knot invariants that come out from this correspondence. So they encode A dependence. Here, -1 is a remnant of T dependence, which is another variable that showed up and is very useful. And of course, Q is our favorite variable that has to do with quantum groups, a generic Q. Now, this object also depends on X. That's also going to be same X. We were using it yesterday. And one thing I should emphasize is that in writing this form, of which I'll only care and explain today, this metric C, that's going to be the object I'll work with. In order to write it in this form and to produce the quiver, it's actually a good idea to have all the variables restored. So even though my goal was to work with SL2, especially in the first talk, and my goal is still to circle back to this example, which involves SL2. So I only have variable Q. To work with the quiver, it's a good idea to restore variables A, X, and T. So even categorified version. So then many more aspects of this correspondence become visible, come alive, and this directly relates to Jan's question about Mativik refinement. Now, let's look at this formula very carefully. It has Q to something quadratic, and again, it has Q-Poheimers in the denominator in some linear terms. So same type of expression appears in completely different field. Now we're going back to vertex algebras. So here is an example paper by Fagin. In fact, two Fagins, Fagin and his son and Tipunin, some of the names you've seen before. And they discuss logarithmic vertex algebras of the type that I showed you on one of the previous slides. And one of their main theorems, which is stated basically on the first page of the paper, it says the main result of this paper is theorem 1, which says that some characters of these logarithmic VOAs can be expressed, and let's look at this formula, in exactly the same form. Q to something quadratic and Q-Poheimers in the denominator, and we're summing over natural numbers or non-negative numbers. So what's going on? Let's look a little bit closer into this and decode some of this statement. So some of the terms originate from physics. Fermionic formulae is obviously physics term. Some quasi-particle is a physics term. But the paper is published in a journal of pure mathematics. So actually both of these terms can be translated into pure math. And where does this structure come from? First of all, the structure has a name. It's called fermionic form of characters, or logarithmic VOA, or VOA characters in old days. And it came from relation between two algebraic structures. On the one hand, vertex algebras, that's where you want to express characters in such particular form. And they're called, again, fermionic form of the characters. And on the other hand, the other algebraic structure has to do with symmetries of integrable lattice models and quantum groups, where you don't see infinite dimensional Virasoro or other algebras on this side. What you see is, for example, R matrix. And the point of this correspondence, which mathematically can be viewed as part of the Kazhdan-Lustig correspondence between this algebraic data and this algebraic data, for instance, you can compare the center of the quantum group and the modular representation on this side, or you can compare the tensor categories on both sides. So that's really part of Kazhdan-Lustig correspondence. So this quasi-particles, which were used as part of the title in this paper, are precisely the states in the R matrix describing the corresponding quantum group. For example, the size of the R matrix or the size of this quadratic form will tell you about different types of these colorings of the strands, which in mathematical physics could be called quasi-particles. So the size of the C matrix in my previous notations is telling us how many quasi-particles we have, or the size of the R matrix in the quantum group perspective. And again, fermionic form simply refers to this form of writing this expression. So everything here is purely mathematical, or can be translated into purely mathematical language, but it originates in mathematical physics or a theory of quantum groups developed throughout 80s. So here are some of the key players which played an important role in this correspondence between VOA structure on the one side and quantum groups on the other side. Are, first of all, several papers by Zamolodchikov brothers, Sasha and Losha Zamolodchikov, in fact, going back to even their joint paper in '79, which was exactly about this kind of correspondence. Then a lot of things happened throughout 80s, so I'm skipping here so many references, which obviously wouldn't fit even on this page, finishing up with developments by Leningrad School, Smirnov, Reshetikhin, and many others, where Youngian symmetries, beta-ansatz equations associated to vertex algebras were recovered. And this is, again, very exciting, beautiful bridge, which mathematically is naturally falls under the umbrella of Kazhdan-Lustig correspondence. Well, let's get a little closer to, so this was mostly 80s, and maybe I should point out that first fermionic form of characters actually appears in paper of Hans Bethe, so that's not a stretch, it's really true. Maybe again, we shouldn't go all the way back because it's only one isolated example, but it certainly was actively studied, this fermionic form of characters throughout the 80s. And of course, appearance of beta-ansatz and Hans Bethe is not an accident. That's, again, same spin chain model that led to the fermionic form. This subject really took off in the early 90s. So previously, I showed you some of the precursors and where it fits in the theory of quantum groups and VOAs. But in early 90s, this really took off thanks to, first of all, developments by Leningrad School, but perhaps even more actively by Barry McCoy and what's usually referred in this community as Stony Brook team. So as you can see, the subject is extremely rich, and for example, here this group of Barry McCoy and other people studied Rogers-Ramanujan identities for these sort of functions, interpreting them as bosonization and fermionization. So if this form of character is so-called fermionic form of character, then you can imagine the right-hand side of this formula written slightly differently. That would be called bosonic form of the character. And that's precisely the subject of this very nice paper KMM in '93. And as you can see, many of these developments indeed go back to early 90s. A lot of things happened in '93 in this perspective. Partly for this reason, it's hard to name this particular form by any single person. If anyone, it may be Barry McCoy, but I think that's he basically pioneered this in modern days of VOA. But again, I want to emphasize that history is extremely rich and goes back even earlier to '80s, which was extremely active period of study of this fermionic form of characters. And especially throughout the '90s in terms of work of Ramanujan and others. And in 2004, roughly 10 years later, Werner Nahm wrote a very nice paper on fermionic form of characters. That's again the same expression we see where Q appears in a quadratic form and Q-Poheimer's in the denominator. And he connected beta equations to elements in the Bloch group. So naturally, this was very beautiful work. And in some circles, therefore, this form, this expression, is referred to as num-sum. And I think people who coined this term num-sum try to differentiate it from fermionic form of characters by rather subtle difference where they want to associate this to element in the Bloch group or something else. To be honest, I don't fully understand the distinction they were trying to emphasize. So therefore, in this talk, I'll refer to all of these three objects very democratically and to be inclusive, and especially nice to founding fathers like Barry McCoy and other people. I'll call it fermionic form of VOA characters. To me, I won't make the subtle distinction with num-sums that probably imply element in Bloch group or something else. We should ask people who introduced this term what they meant. And also, I hope you see now that there is a connection to quiver generating functions. That's going to be important. So when I started working on the subject with Piotr, I asked him what's the difference. And at first, I'll be honest, I didn't fully see the difference between structure of the quiver generating series and then this fermionic form of characters. They look to me the same. But now that I learned what it is, I can summarize it for you. So first of all, conceptually, representation theory is quite a bit different. Here we talk about representations of quiver algebras, and here we talk about vertex algebras. They're encoding completely different things. So here we're just taking trace of a certain VOA module, for example. And here they have to do with enumerative invariants, as we saw, and various other cool things. Secondly, VOA characters typically have just one variable Q. You can introduce other variables if vertex algebra has symmetries, but at least in the standard form of work of Barry McCoy, Werner Nahm, and many others, including some homological brothers and so on, you just have variable Q. Here, as I try to emphasize in the world of quivers, not only you can introduce additional variables quite naturally associated to the quiver data, but actually that's a good idea. You should introduce variables A, T, and many variables X, which encode the rich quiver structure. So they're different, both in terms of representation theory and in terms of variables that they involve, but important point is that there is an overlap. In particular, if you specialize A to Q squared, for example, which is what I want to do for this Z hat invariant, you actually go back from many variables to just one variable Q. And that's where you can interpret this sum, Barry McCoy sum or num sum, as a fermionic character of vertex algebra. That's going to be the punchline of this talk. And in the remaining few slides, I'll try to illustrate this. There is a subtlety, however, that not quiver correspondence was originally developed for so-called conormal quivers. So it packages Home-Flea PT polynomials, and the reason it's called conormal is that in the enumerative geometry, what's relevant is a Lagrangian submanifold in Calabi-Yau, which is produced by conormal construction of the knot. What we need for the Z-hat invariance is a slightly different version of a enumerative problem, which involves three manifolds, also realized as Lagrangians in Calabi-Yau, but they are not complements rather than conormal three manifolds. So this required a little bit of work, which was pioneered by Piotr Kucharski. And then we studied this in a very recent paper with many collaborators, my friends over here. And the upshot is that for this variant of the problem, you can also introduce quivers in very much the same form. In fact, you can construct these quivers out of the old quivers. I probably shouldn't call them old because they're only 5 years young, but anyway. The point is you can produce the same form for this invariant for the knot complement that we introduced with Ciprian and then generalized in later work, and produce the matrix C, which is again going to be the star of the show or main ingredient today. More so, what we found in this recent work is that not only you get one quiver, but you get one quiver per every side of the Newton polygon of the A polynomial for the corresponding knot. So there is a close relation between so-called branches of the A polynomial of a knot. So here is an example for the trefoil, and the sides of the Newton polygon, say, viewed from the left. So one of the sides, which is vertical, always corresponds to the abelian branch, and that's the one which we need for Z-hat. So this matrix is going to be very relevant. But you can also associate quivers and the corresponding fermionic type sums or quiver forms of partition functions to the other sides, for example, to this non-abelian branch of the trefoil knot. That's this term. For the figure 8 story, you get something similar and even more interesting. The figure 8 knot famously has 3 branches of the A polynomial curve. This is curve A of xy equals to 0. This is a abelian branch that's related to Z-hat and things I was discussing yesterday. And in terms of the Newton polygon, it's this vertical face of the Newton polygon. But now there are 2 other branches corresponding to geometric and conjugate branch that are related to generalized volume conjecture on this side and the cumulative QFT on this side. And for all of them, you can produce corresponding quiver forms or fermionic forms or whatever you want to call them. So now specializing all the variables, in particular going through this long path of going to a variable and enumerative geometry and then setting in the end a equals q squared, you actually get something that depends only on q for the knot complement, in this case of the figure 8 knot. You can see that this structure is not really messed up by the Sergei formula. So the Sergei formula produces, if an input is of this form that depends on x, remember yesterday we were doing a bunch of integrals where x's are integrated out. So the result also comes out of this form with only variable q, x's disappear, x is gone. And the metric C is just slightly different. It's a little bit deformed, but the general structure still remains the same. It's the sum where you're summing over non-negative numbers di, in this case 6 of them for this particular expression, quadratic metrics that can be obtained from the quiver for the knot in a very quick systematic way. And you have Kuperheimers in the denominator. So now I guess we can repeat the question. Is it a num sum or is it the fermionic form of VOA character? Well, you probably guess what connection we can now make. This connection between quiver forms and fermionic forms of VOA characters, of course, is very meaningful. It immediately allows to reinterpret this expression as a character of some vertex algebra. In fact, a character of logarithmic VOA, the way I advertised it in general conjecture. And now I want to finish this talk, this connection, going through quivers and curve count, circling back to Z-hat and this Q-series invariance over here. It opens door to many, many questions. And in particular, not only can you now compute this Q-series expressions to very high Q powers and do many experiments or study three-manifold invariants, verify that they're integer, or even try to categorify them. You can now try to see connections to this VOAs, something that has not really been explored extensively. Having this fermionic form of z-hats, which could be called again as Berry-McCoy or a num-sum form, is extremely useful for this comparison, for identifying this Q-series invariants with characters. And the basic question you can ask is, what's the growth of the coefficients? Because this will relate to basic quantity of the vertex algebra, namely so-called effective central charge. And something that's a little funny to me is that if you experiment with simple examples, coming from different types of manifolds, ciphered, hyperbolic, and so on, in many, many examples, you find that this effective central charge is equal to 1. So in early days, I was wondering whether we can even make a conjecture that it's always 1, or rather it should be equal to the rank. So for SL2, it would be 1, for SL3, it would be 2, and so on. But then my friends quickly pointed out to me that we cannot expect this in general, even for rank 1. So there are definitely corresponding logarithmic VOAs and these z-hats, which correspond to characters of vertex algebras where C effective is not 1. So what is going on? I have no idea. I'll just pose this as a question to the audience, and I hope by now I convinced you that not only this is a subject about Q-series, spin C structures, and Rokhlin and Turaev, but it also connects in a very meaningful way to vertex operator algebras and enumerative geometry and various other fields. So thank you for your attention.
Thank you very much. Let's thank Sergei for the fantastic talks. Questions?
Yeah, Sergei, just a small question about this conormal versus complement. If your knot is, say, algebraic knot, which sits, say, let's your three-manifold is just S3, yeah, so then you have this large and duality story, yeah, and you can convert the computation on the Gromov-Witten side after large and duality into using this Gromov-Witten equal Gopakumar-Waffa, Donaldson Thomas, you can convert it into the question about the knot in the complement of a three-sphere, which is a small neighborhood of a singular curve in C square. So, which means that you converted conormal, which is Lagrangian and the conormal to your knot in three-dimensional sphere into another knot, which is into the question about the complement. So then, I mean, it looks like you can avoid quivers in this translation. So I'm just asking whether you can do it in general, just staying with the geometry.
I think the answer is yes. Something I briefly mentioned, and maybe I should elaborate on this, that in the paper with Turaev and Waffa, we were again highly motivated in constructing the z-hats, for example, by it's supposed to be based essentially on the Waffa-Witten theory for algebraic surface that has a three-manifold on the boundary. So if your knot is algebraic, for example, you can imagine analogous story for the curve. So that would be complex dimension 1 rather than complex dimension 2. So I think the answer is yes. So you can probably formulate both z-hats for closed manifolds as well as this two variable series with x and q variables for not complements in terms of sheaf counting on something one dimension higher that fills in either 3 manifold or the not. And that indeed was part of the original motivation in GPV. Yeah.
Is it always kind of this generating function of the Euler characteristic of transversal slices for 3D unequal for Coulomb branches of kind of okay? Is it always Euler characteristic of a transversal slide and the fine Grassmannians? Let me just shorten.
I don't know. That's a great question that connects to this other motivation. And yesterday, I gave you a definition of this z-hat based on Rosansky-Witten theory with either fine Grassmannians or their slices if you want to go to roots of unity. So that's a great question. I don't know, in part because in 3 dimensions for these Coulomb branches, there are always dualities such as symplectic duality and mirror symmetry. So it's even if something does not look like it, the answer is going to be yes. It's most likely yes and in some dual form. So one has to be careful with these dual descriptions. So I don't know. That's a great question. In fact, I would love to know, and if you're interested, we should probably chat longer.
Okay. Yeah. All right. Okay. Thank you.
Other questions?
May I ask you one question? So, I mean, when your 3 manifold is an algebraic link of some surface singularity, then can I mean, like Homology polynomial, can I describe your invariant as some integration of a Hilbert scheme on this surface singularity?
Yeah, that's what I mentioned to in reply to Jan's question, and also when I was talking about analogy with or what we used in GPV, the paper with Pavel and Kumran on definition of this invariance. So this was very first step. So we were actually relating it directly to Eichler integrals of sheaf counting on such surface singularities, but at that point, we had only a couple of examples, and I think it would be great to study this further. So I was recently discussing this with Ludmil and Joseph. So I think that's a great question. So this is something that needs to be investigated more systematically. But yes, it was exactly the original motivation. Yeah. So.
Thank you. Thank you.
Other questions?
Can I have a comment? You mentioned these two, in a sense, classes of this generating functions. One we called quiver, another fermionic or so. And it was somewhere just a bit later. Yeah, you mentioned that this quiver seems more general because it has more variables. But I'm not so sure, because in this fermionic there are also these linear terms. I think you mentioned them earlier.
Exactly. Yeah.
So one can adjust these linear terms and just redefine Q to some coefficient of that linear term as something also general. So it seems to me they may have roughly the same amount of information.
Well, not only redefining, I think it's conceptually that VOA can have symmetries, global symmetries. In that case, these variables appear very naturally. So yeah, that's why, I mean, if we follow history, we should refer to them as fermionic form of characters. And again, that's based on developments in 80s. Again, I don't know if any particular person should be singled out for the name. So that's why I myself prefer to be very inclusive. That's very important. And especially again, to all walks of life where this was introduced, and be completely democratic about the use of these terms. Yes. But I should also take this opportunity to thank you for introducing me to this subject of knot-quiver correspondence, where I learned a lot from Piotr and other collaborators.
Well, thank you for collaborating as well.
Thank you from Warsaw. Any other questions?
Can I ask a question, but just
Sure.
show the page where you make some correspondence with the integrable lattice models? And yes, so in the left-hand side, you have a dependence on the spectral parameter, which means that on the right-hand side, you have taken some limit or so.
Yes, that's why I was saying that these two sides are not just identical. I mean, they're completely different, and they share a little bit in common. So on vertex algebra side, you have infinite dimensional algebra, which involves Virasora. There is no Virasora anywhere on the left-hand side. Similarly, so it's some ingredients are simply absent. So that's what I'm trying to emphasize. Similarly, if you have spectral parameter on this side, to get to data of vertex algebra, usually take a limit. That's what Fedor Smirnov and others were doing, where a spectral parameter goes to plus infinity or minus infinity. That's how you recover the R metrics. So R metrics, they share in common. That's part of this Kazhdan-Lustig package. But spectral parameter itself does not have to be visible on this side. So
yes, but on the left-hand side, you have a more general object which goes to the characters on the right-hand side. So the question is, aren't there some, I don't know, quantities which are interesting also with a dependence on some spectral, that is, which are relevant for integrable theories and not for their critical limit, so to say? I mean, there is an object here on the left-hand side,
that's right.
From which you get these characters on the right-hand side.
That's a very good question. So, right, so posed this way, a little bit broadly, it's a great question. I know only some coincidences sometimes. For instance, spectral parameter can be interpreted as variable t in some cases. So it barely appeared yesterday, and today variable t was more prominent. It had to do with for instance, this homological gradings and other things. So sometimes that seems to play the role of spectral parameter, but that's a great question. I think it has to be investigated further. And as of course, you know very well, there are many connections between algebras such as Youngians and Bethe-Ansatz equations encoding the data, some data of the CFT. So I think you're asking a very good question. Yeah.
Okay, thank you.
Other questions? If not, let's thank Sergei again for the wonderful talks, and the conference proceed at 2 p.m. Thank you very much. See you soon.
Thank you all. Thank you.
Thank you, Sergei.